Some of you are in here when I said it, some of you weren't. You think it's funny. I think it's ridiculous. So I'm the boss. You watch it. You leave that block open. Don't mess with it when you walk in because you think it's funny. If I catch you, I'm going to beat you. You leave it alone. All right. One thing, and I realize I'm live right now, and this is whoever's going to watch it's going to go, what? Check your calculators and see if you've got some charge on it. I am not going to issue you guys a charging cord. If you need to have it charged, you're going to have to leave it here maybe for the day and come and get it afterwards or something. They only need to be charged about once every 2 months. They hold the charge a long, long time. And then his battery's up in the top, and you should have a little bit of green in it, at least right now to start. Yeah? Everybody got a little bit of going for you? Okay. You won't need this for a few minutes, so turn it off. Make a habit when you're not using it of just hitting the second and the off. Y'all know how to turn it off, right? There's no learning curve on these. They are faster. They're backlit. They're rechargeable. They have a higher resolution on the screen, so you don't have all the little jerky little steps. They're color. They have more memory, but they are the same keypad. So I'm going to keep using that poster up there. That's the old ones. Keypad's the same. Okay? Everybody okay with that? There's no learning curve. If you've used the other one, this one works the same way. It's pretty. That's all. And it's more expensive. So you'll be paying more to replace it. All right. Page 238, section 5.1. One more comment. For those of you who were in my class before, if you scored 75 or better on the final exam, you are eligible to use big ideas for this chapter. And everyone who is in my second part, everybody that was in my class before that's in this class, managed to do that. That's excellent. So everybody in here for the first chapter can do their assignments on big ideas math if they want, or you can do it on paper from the book. I don't care which one. But when you take the chapter 5 test, if you do not score 75 or better on it, you have to do your assignments on paper for chapter 6. Y'all follow what's going on? Yep. All right. Because I'm concerned if you're not getting enough out of doing the information on, or doing assignments on big ideas, if you're not doing it well enough to at least get a middle-sized C, then you need to start doing it on paper so I can help you more and see more about what you're doing. So that's why I'm doing it. It's not a punishment, because I want to be able to get things done right. All right. I told you the page number to go on. You don't need to turn back if you don't want. But this chapter 5 is called, way back here, it's called Rational Exponents and Radical Functions. Yeah. Six sections. We're going to do them all. Section 2 is going to be split up into 3 pieces. It's going to be a 5.2a, 5.2b, and 5.2c, because it's got a lot in it. I want you to have plenty of practice. But this, the title of this, Rational Exponents and Radical Functions. I got a feeling you probably have got an idea what exponents are. But do you remember what rational means? It shows up in math all the time, and people don't even know what it means. They just gloss over it. What does it mean?
Isn't it every number and 0?
Those are whole numbers. That's
okay.
Yeah. They're not quite the rational yet.
Real numbers.
Real numbers are beyond the rationals. Anybody describe what a rational number is?
Not like a numbers less than not a fraction.
Numbers less than 1 are just half the integers.
So negatives.
No.
So is it 0 and above with partial numbers?
Nope.
Is it 0 and below with partial numbers?
Nope.
That's your way.
Listen, I'll give you the definition of a rational number. You should learn this really, really well. You really should. For those of you who've seen my diagram before, I don't think I'll put it up here today, but there are the natural numbers, which are the counting numbers. That's what I count you. That's how I'm going to count you to find out how many of you are here, and then subtract how many are supposed to be and tell you how many are missing. That's counting. Then there are the whole numbers, and it's only bigger by 1 element. It's the counting numbers with the number 0 on the front. Then there are integers. And they're all the whole numbers, including the negative ones. They're all whole, no fractions. Then there are the rational numbers. And it is the fractional part of that set that makes them distinguished from integers. And here's its definition. Try and hear me. what I'm saying. A rational number is any number that can be written A over B, where A and B are integers. And integers are the whole numbers, positive and negative. So for example, -2/3, that's a rational number. Because 2 and 3 come from the set of integers. -4, that's a rational number. Because -4 and 1 are integers. And you can write -4 over 1, right? Those are integers. The one integer that you can't use is 0, and the only place you can't use it is in the denominator. So when I say any integer, or excuse me, a rational number is any number that can be written A over B, where A and B are integers, you have to put this little thing, this little, and B is not 0. You can never divide by 0. A could be 0, but B can't, but the denominator can't. So really, when you see the word rational in any title to anything in math, you're going to be talking about fractions. Because it is the fraction part of that set that distinguishes it from the whole number integers. That's what makes it the next bigger set. So whenever you see the word rational, you're going to be talking about fractions. Now, what does the word radical mean? Not in common language, but in math, yeah?
Square root.
Exactly. Radicals, what he's saying right there, and I kind of cut him off, but what he's saying right there, radicals are symbols like this. And like this, you're going to learn today. Put a little thing in the hook, it's called an index. Now we're not square rooting. Square rooting is an understood 2. We use it so often we don't bother to write it. It's just an understood 2. But we also have square roots. We also have fifth roots. We have cube roots, we call them. They look like that. You're going to see them all today. Every one of these symbols with the little hooky thing that goes over, looks like a division symbol, but it isn't. The thing and the stuff that's underneath here is what you're going to affect with this radical symbol. It's a radical symbol, okay? So what we're going to discuss in this chapter, based on the title now that you know what's going on, we're going to be talking about exponents that are fractions and an awful lot of those radical symbols and how to deal with them. Exciting, huh? But too bad. Here we go. 5.1, the title to that one is called nth roots and rational exponents. So it looks like we're going to study it all right today, and we are. We're going to get our feet wet. Nth roots was what I was just talking about. When you have nth roots, it means like fifth roots. That's a fifth root. And n would become 5, so it would be fifth root. Cube roots. We don't say third roots. I've never heard of that. It's called a cube root. This is a 10th root. Are you going to get that high? Probably not. But we're going to have all sorts of indexes in here, and we would call this, instead of just nth root, that's just a way of lumping them all together. We got fifth roots, cube root, 10th root, 8th roots, 4th roots. And it's what sits in the index. And we're going to talk about how you deal with that, what it means. Okay, so that's your nth root idea. Now here we go. Look at the core concept on page 238. This is really important, and you may want to refer back to this. I'm going to read it with you, and then I'm going to explain it to you. It says real nth roots of A. Nth roots of A. You'll see what that means in a minute. Let n be an integer greater than 1. That's how you read that if you're fluent in math. You don't say n, well, I guess it does say n greater than 1. So let n be an integer. That means a whole number, people. That means there are no fractions. Let n be an integer that's greater than 1, and let a be any real number, like any decimal or pi or the square root of 2, or let it be any real number you've ever encountered. Here's what it says. If n, that's your root thing. That's the n. If n is an even integer, and the thing that you are rooting is less than 0, there won't be 1. This is weird. All this stuff, you just got to get it in your head. You got to get the notation and the stuff in your head to see what's going on. What they're saying is, if we have, for example, the of -5, 54, we'll say, the fourth root of negative 54. What it means is to find a number that if you multiply that number by itself 4 times, gives you negative 54. There are no such numbers, not real ones. And that's all we're going to be discussing today, real ones. Why is there no such number? Because when you multiply 2 numbers together, these are all the same numbers, by the way, all 4 of these, they're exactly the same number. If you multiply a number by itself, if it's negative, and you multiply that same number by itself over here and it's negative, you get 2 positives. Positive times a positive is a positive. You can't get 4 things to multiply together if they're the same thing and get negative. It can't happen. You learned that with square roots. For example, if you were going to try to square root 25 or negative 25, the answer is no solution. Because you can't find a number multiplied by itself that gives you a negative. Doesn't happen. Not in the real set. Now, I know you guys will go, well, that's 5i. We're not talking about i's today. We're looking for real solutions. So does it make sense to you that if I put this, remember, this is a 2 here. We're understanding that's a 2. Both of these are even. That you cannot even root a negative and get anything real? Does that make any sense to you? Really? You're just nodding at me, so I'll leave you alone. You cannot even root anything that's negative because there are no numbers that multiply by themselves an even number of times and get a negative. So this is also undefined. That's what that very first line of that core concept says. That's all the farther we've got. It says, if a is less than 0, in other words, if a is negative, this is a. This is the thingy that you're rooting. If it's a negative, the thing inside the radical is a negative. That's what they're saying. And n is an even integer. That's the top of the column. Then there is no real root. That make sense to you? You understand those words or not? You get it? Okay. The next one in that column says if a is 0. So the thing we're rooting is 0. If you take an even root of 0, you'll get 0. Because guess what? 0 times 0 times 0 times 0 is 0. Okay? If you 10th root 0, you get 0. Duh. Right? The next line says, if a is positive and n is even, we're still in the even column. If a is positive and n is even, you will get 2 solutions. They may not be rational solutions, but there will be 2 of them. For example, if we 4th root 81, we get 3. If we 4th root 28, we don't get 3. Oh, by the way, sorry about that. I lied. Hang on just a minute. Hang on just a minute. There's a different way of writing this. I kind of screwed up already a little bit. When you put this symbol, this is really, really subtle, and I really need your attention here because you're going to mess this up if you don't pay attention right here. When you actually use this symbol called a radical symbol, this hooky little symbol here, and you wrap it around a number like this, they're only asking you for the positive roots. If this thing is, if these are even and these are negative, you get nothing. But what I'm saying is, if I ask you, for example, to find the square root of 9, I am only asking you for the number 3. But if I ask it this way, if I say find the square roots of 9, the answer is plus or minus 3. Or if I say find the values of x, where this is true, you square root both sides. Yes, that's what you do, but you get plus or minus 3. Why? Because 3 times 3 is 9, but negative 3 times negative 3 is also 9. So why don't we do this? Because this symbol right here, this square root symbol, has a very specific meaning. It's called find the principal square root of 9. Principal means the positive one. So when you see a symbol in your book and it says evaluate or find the value, and they put a hooky symbol on that, a radical symbol on that 9, you answer 3. But if instead they phrase the question, find the square roots of 9, you got to have them both. Or find the values of x to make this true, you got to have them both. It's very subtle and very crazy, and there's a reason for it, which we will discover a little bit later. But if they put a symbol on it and ask you to evaluate this, and this is how they present the problem, you give the principal square root of 9. Okay? So take a look, for example, at how they're asking. It's kind of subtle and kind of tricky. But look at how they are asking you to do, I gotta go over the odd ones first. Hang on just a minute. We're not done yet. But when they ask you to find the square roots of, or the cube roots, or whatever of a particular number, they ask it this way, you've got to give them both. So if I do something like this and I ask you to find the fourth roots of 28, do you know of any number when you multiply by itself 4 times it gives you 28? I don't either. I really don't. But your calculator does. How do you do a fourth root on that calculator? How do you evaluate that? How do you find the number multiplied by itself 4 times that gives you 28? Any idea?
28 to the 1/4.
Yeah, that's what we're going to learn here in just a minute, but it's useful to tell you right now. This expression right here is exactly the same as 28 to the 1/4. In your calculator, the syntax means the way we actually enter it, you would write 28 and your caret key and either the number 0.25, since that's 1/4, or put a parenthesis and write 1 divided by 4. And it's a pretty ugly decimal, right? It's an irrational decimal. Can somebody give it to me to approximate? By the way, folks, here's another thing. If you write an equal sign with a dot on it, it means you know, as the doer of the problem, this is an approximate answer. Give it to me to 3 places.
2.300.
Okay? There's other numbers after it, but we got it to the nearest thousandth there. Now, is it still sitting in your calculator?
Yeah.
The answer, with all of its decimals and ickiness, it looks awful. It's an irrational number. Take that number and just go, whatever it is hit raise to, and it will say answer. It'll type answer for you and a raise to symbol if you just hit the raise to. And raise that to the 4. See if that doesn't get you back to 28. Yeah? So it makes good sense that 1/4 got the number. See, this number multiplied by itself 4 times is 28, if you had all its decimals. And if you raise that number and multiply by itself 4 times, you get back to 28. So that's good evidence that you did it right. You following? Okay. And it is only that one number because I asked it to you with this symbol. Had I asked you for the fourth roots of 28 and asked it to you writing it like that, you would have written plus or minus 2.300. Even though your calculator only gave you 2.300, because you, in your calculator, you asked it to do this and it only gives the principal square root. You have to know if that it's asked this way or you're solving an equation that you put the plus or minus on. We good or not? Lots and lots of details here. Okay, moving on. Let's look at when n is odd. When the number in the little hook is an odd number, you're going to get 1 real and 1 real and 1 real in all 3 conditions. If, for example, the a is a negative number and we want to take the cube root of it, you're going to get 1 real solution and it will be negative. If it's equal to 0 and you odd root it, you'll get 1 real and it's 0, just like any other thing. If a is positive, you will get 1 real 0. And it'll be positive. Let me show you what I mean. If we take, for example, let's take something small. If I take the cube root of negative 27, what I'm looking for there is a number that I can multiply by itself 3 times, the same number 3 times, and get negative 27. And that's quite reasonable because even if the number is negative, I multiply the first 2, I get a positive, but I multiply by the last one, it's going to be negative for an answer, right? That's the reason why if you're cube rooting a negative, you will get a negative. Negative 3 times negative 3 is positive 9. But positive 9 times negative 3 is negative 27. So if the index is odd and this is negative, your answer will be negative. What about this? What if I ask you to find the cube roots?
Wouldn't it still be only negative 3?
It will be. What if I ask it to you this way? If I ask you to find the cube roots of negative 27, the answer is still just negative 3. Why did we get 2 answers when we did stuff like this over here? Because a negative times a negative is positive. Over here, a negative times a negative times a negative is negative. And that's all it can be. It's just negative. So you only get one real, no matter how you ask it, if this is odd, or if this thingy right here indicates an odd. If I ask you to find the fifth roots of 32, that's just 2, positive 2, and it can't be anything else. Because 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Took 5 2s to multiply to be 32. And since 32 was positive and this was odd, your answer is positive. Even if I ask you to find the fifth roots of 32, the answer is still just 2. Because if I put plus or minus here, that would indicate that 2 times 2 times 2 times 2 times 2 is 32. And so is negative 2 times negative 2 times negative 2 times negative 2 times negative 2 is 32. And it isn't. Negative 2 5 times is negative 32. So it's not a plus or minus here. You see the difference? Okay. Let's take a look at the first example.
Miss J.
It says find the indicated real roots of A.
Miss J. So why, for the first example with the negative 27, so why is it not an imaginary solution?
Because when you put that radical symbol over negative 27 with a 3 in the hook, it's saying, find me a number such that when you multiply it by itself 3 times, the same number 3 times gives you negative 27. And negative 3 times negative 3 is 9.
Yeah.
Times negative 3 again, negative 27.
Okay, so it's just asking for the.
Yeah, that's down, right down at the nitty gritty. What that radical symbol asks you to do is it's saying, find me a number such that when you multiply by itself, the index number of times, 3 times, will be negative 27. And negative 3 fits that bill.
Yeah.
You understand?
Yeah.
That's why it's not imaginary. This one says, if I was to do this, for example, I'm changing the game here a little bit, but if it says, find me a number multiplied by itself twice that gives you negative 9, you won't be able to find one that's real.
Yeah.
You understand?
Yeah.
So this is not defined, not over the real numbers, which is all we're working with today. You understand?
Yeah.
So we can get something when we odd root a negative, but not when we even root a negative. Very clear? Okay, good question. All right. So let's take a look at the examples that they've got there, and let's see if we can answer them. I probably shouldn't have erased that yet, but I'm gonna. Okay, example 1 says, find the indicated nth roots of A. Notice that there's no radical symbols in the asking of this question, which means we got to find all of them. If it requires a plus or minus, we got to have it. So it says, find the indicated real roots of A, and it says n is 3, and A is negative 216. So this is what they're asking without really writing it out. They're asking you to find n is 3 of negative 216. First of all, will we get a real answer out of this?
Yes.
Yeah.
Well, yeah.
Will it be positive or negative?
Negative.
How many will there be?
1.
And it will be
Negative 6.
negative 6. And you can find that out on your calculator, or you can remember the perfect cubes I wrote for you guys. You became familiar with them in my last class. B says n is 4 and A is 81. What they want is this. Now, this is a method for doing it. Notice there's no radical symbol, but this is how we're going to accomplish it. The fourth root of 81, I know I wrote it as a radical symbol, but they didn't, which means they want them both if there are 2 and there are 2. What is it?
Plus or minus.
It's 3 and it's plus or minus because it's even.
Yeah.
I just happened to use the symbol, but they didn't ask it with the symbol, so we gave both. You see what's happening? They ask you for the nth roots. All right, moving on. Rational exponents. That's what we just discussed a little while ago. Rational indicates you're going to be doing what? Working with what? Rational.
Fractions.
Fractions. And we've already seen one use of it. For example, if I wanted to figure out what this is in a calculator because I didn't know what it was, you would say 81 raised to the 1 divided by 4. That's what that indicates. We're going to use the reciprocal of 4 when we're fourth rooting. So we've already seen one exponent that's a fraction. I guess what I'm saying is that this is the same thing as 81 to the 1/4. All of these mean the same thing. Okay, so we've already seen one fractional exponent, but we call it a unit fraction because there's a 1 in the numerator. But there are all other kinds of fractions, like 2/3, 7/4, stuff like that. And so now we're going to discuss those for a little bit. A rational exponent does not have to be of the form 1 over n. Other rational numbers such as 3/2 and -1/2 can also be exponents. 2 properties of rational exponents, means fractional exponents, are shown below. These are important. And it's hard to get used to. It says, let a to the 1 over n be the nth root of a. We already discussed that. It's the same expression. And let m be a positive integer. Now we're gonna say, what's a to the m over n? That would be like saying this. What is 32 to the 3/5? That's a similar thing. It's a number that we're going to power, and the power is going to be some fraction. I'm going to work with both of these so you can see something concrete, something not. This is the same thing as the nth root of a to the m. This right here is the same thing as the 5th root of 32 to the 3rd. They mean exactly the same thing. And I don't know if this is going to help you or not, but I'm going to draw you a little picture to help you, maybe give you a mnemonic for remembering which one goes where, which of these numbers goes where, whether it goes here or here. It's kind of silly, but silly things tend to stick in your mind. I don't know if it'll work. So here's the ground, we'll say, and here's your house. Not a great artist, so don't hold me to this. Okay, and you got power lines out here, and the power's coming in to the line like this, and it comes over here. And then there's some sort of receiver on your house, something it's hooked to, and it comes in like that, right? And you get power's your house, right? So I'm going to call this up here power coming in. This is power. And then somewhere in the backyard, maybe the front yard, as long as it doesn't interfere with the power lines, you've got a tree back here. And the tree has roots. These are roots. The power is over the roots. Power is on top. The roots are below. Power is on top. See the power? Power is in 3. That's the power on 32. The thingy that goes, or the root, we call it the nth root, that goes in the index. So if the power, if you have a fractional exponent, the power part of it is on top. That's the exponent on the inside. The root, or the index, the root thingy that goes in the hook right here, that's on the bottom. Okay, kind of a dumb little mnemonic, but it may help you remember, because whenever you have those two numbers, people go, I can't remember which one goes where. Okay, so power is the top one, or the numerator. Roots, the root one is at the bottom. So this translates to this. It's a different notation, okay? All right, I need to remind you of something else. If you have a negative exponent, like, let's say you had 8 to the negative 2/3. That's the same thing as 1 over 8 to the 2/3. Which is the same thing as 1 over the cube root of 8 squared. Yeah, you see it? Okay, so if you have a negative 1, you put it where it's not. Now, by the same token, people still mess this up sometimes. If you have 1 over, let's say, 27 to the 2/3, that's the same thing as 27 to the negative 2/3. When you bring it up, basically bringing it up in the numerator and leaving the 1 in the denominator. You flip that over, you're going to get a negative exponent on it. So sometimes that's important and necessary. So if it's down below and you put it up, the sign on its exponent changes. If it's up above and you put it below, the sign on the exponent changes. All right, so that's what they were going to say over here. A to the negative m over n is equal to 1 over the nth root of a to the m. Okay? Y'all following this? All this notation? Okay. See if we can do a problem here. It says evaluate each expression, 16 to the 3/2. Got to evaluate, which means find the number that is this. And I know you can do it in your calculator, and that's how you'll survive on your test, probably. But I still want you to have a sense of this, so I'm going to walk you through it. 16 to the 3/2. 16 to the 3/2, and you could just put that in your calculator. And I know you can, and I know that's what you're going to do. You're going to do it on your exercises too, because you're lazy. You don't want to have to do this. But this is how I would do this, because I'm not lazy, and I know this really well. I can tell you what this answer is right now, 64. And here's how I know, because I'm going to square root 16. which is 4, right? And then I'm going to multiply 4 by itself 3 times.
So it doesn't matter the order which you do it?
Oh, it matters. This, remember, that's the radical. That's the square root. And this is of 16. And I'm going to square root the 16, and whatever I get, I'm going to cube. Now, that isn't what I just wrote just a minute ago, but it means the same thing. I mean, it's exactly the same. So let me write something that they didn't write in the book so that you understand this too. You can, if you have a to the m over n, you can write that either as the nth root of a to the m in here, or the nth root of a to the m out here. It doesn't matter. It's the same thing. And that's what I choose to do, because I can square root 16. I don't want to square that. I don't want to put this 3 in here. I don't want to cube 16 and then square root the result. I don't want to do that, because I don't know what the cube of 16 is. But I know what the square root of 16 is. It's 4. And I know what 4 cubed is. It's 64. Check it out in your calculator. That answer is 64. So this is how I see it, because I've had a lot of experience with it. When I see something like this, I think square root, that's 4. Now I'm going to use 3 of those 4s. 4 times 4 times 4 is 64. That's what that literally means. Square root 16, and whatever you get, multiply by itself 3 times. Okay? I'm going to show you something else too. If you like this, and some of you will grab onto it, many of you won't, but some of you will. You can also think of it like this. You can think of it now. There's a lot of you that I've had in my class before that know how badly I hate mixed numbers. I hate them like 7 1/2. I hate those numbers because they're useless for doing arithmetic. You have to always change it to an improper fraction first, so just leave it that way. Here is one case, if you buy into what I'm about to tell you, where mixed numbers can be very useful. Because 16 to the 3/2 is the same as 16 to the 1 and 1/2, right? So what this literally means to me is that we're going to take a whole 16 and multiply it by the square root of another 16. That's what that means. 1 whole 16 times the square root of 16. That's 16 times 4, which is also 64. So if you have something like this and you have, just to show you how that works out, if you have, let's see if I can do this right. I'll say 8. It's an easier number to work with. 8 to the 8/3. That's the same thing as 8 to the 2 1/3, right? Or 2 2/3. What that says is that I want to take 2 whole 8s and multiply it by the cube root of 8 squared. That's 64. That's 8 times 8 is 64. This, what's the cube root of 8? Squared is
4.
So I'm going to take 8 times 8 times 4. I want to take 64 times 4, which is 256. Or you can just power it this way if you're lazy. But there's all sorts of cool things going on here. Okay? Depending on how you want to look at it. So take a look at the next one. It says 32 to the negative 3/5. So that's the next problem. We're going to use this on right here. 32 to the negative 3/5. That's the same thing as 1 over, if you'll jump and make all these leaps with me all at once. It's 1 over because it's negative. The 5th root of 32 cubed. Goes in the index, goes downstairs because it's negative. There's the 5th root, and I'm going to use that 3 as the power. What is the 5th root of 32? Anybody? 2 cubed? 8. This is 1/8. The answer to this whole question is 1/8. We pushed that downstairs because the exponent was negative. We turned it into a radical, and we took the 5th root of the number, and whatever we got, we cubed it, stayed in the denominator. Okay? And also use your calculator, but it will give you, if you do this, if you write it in like this, it'll give you 0.125. Do you all know how to convert decimals to fractions in your calculator, if it's possible? Yeah. Math, enter. Have you all done that? So what you can do if you're lazy or you want to check, if you're just lazy about this, you can take 32 in your calculator, raised to the -3 divided by 5, and it will give you 0.125. Then you can hit math, enter, enter, and it will give you 1/8, which will get you that if you're a button pusher. But this is the math, this is the reasoning behind it right here. You fifth root 32 and cube what you got, leave it in the denominator. All right, moving on. 2 more examples, we're almost there. Example 4 says, find the real solutions of, and it gives you 2 equations. We're going to do them both. They're separate equations. They're not involved. They're not tied together at all. I've got 4x to the 5th equals 128. Four x to the 5th equals 128. Now, the process for solving this equation is to first get the x to the 5th all by itself. Do not try to apply that 5 to that 4. It only applies to the x. It is not 4 to the 5th. It is 4 times whatever this number is to the 5th. So we need to get rid of that 4 first by dividing. We get x to the 5th equals 32, and we've done this before. So now we 5th root this because 5th rooting x to the 5th is x. We 5th root this and we get 2. Just 2 or plus or minus 2? Just 2, because that's odd. If it were an even index, or an even power, we would get plus or minus. So take a look at the next one. We get x minus 3 to the 4th equals 21. It's in parentheses. Now, if you want, this would be gross. Think about what would happen if you follow your instincts on this. A lot of people look at that and go, oh my gosh, oh crap, I got to write x minus 3 out 4 times and FOIL it all together and then bring the 21 over and try to refactor it. No, don't do that. Just 4th root this side. It gets rid of the power. But you got to 4th root this side too, which is plus or minus root 21. You're going to leave it like that because there is no number that you multiply 4 times that gives you 21. That's rational anyway. Your calculator will give you an answer, but I don't want it. I want this in exact form. So we 4th root this to get rid of that 4. That gives us x minus 3. You 4th root this, it doesn't 4th root nicely, so leave it. And it's an exact form. Why do I put a plus or minus? Because that's even. Because we're even rooting, so we have a plus or minus. Then kick the 3 over to the other side, and it's customary to stick it in the front like this. And that's done. Because it's in exact form. We can't 4th root 21, so we'll leave it in its radical form so that it's exact. Otherwise, it would be irrational. If we add 3 and subtract, or take 3 plus it and 3 minus it, it's still going to be irrational. Mathematicians like exact things. And I know that looks ugly, but it's prettier because it's exact. So if it says leave things in simplest radical form, if it doesn't square root or 4th root out, leave it alone. Notice that the author gives you both solutions at the bottom of that thing. He says the solution is approximately 5.14 and 0.86. So if they ask you in the big ideas math or in the instructions in the book and they say round to the nearest hundredth or something, then you do have to turn this into a decimal. Do you know how? Let's everybody practice turning that into a decimal. It would be 3. This is what you type in your calculator. 3 plus 21 raised to the 1/4. That's how you would convert the plus one, the plus piece. And then you would round that to the nearest hundredth if that's what it asked for. What is it?
5.1406. Yeah.
Okay, that's good, to the nearest hundredth, right? Okay, and then you would do this one. And here's a cool thing you can do with your calculator. You already typed that. It was took you a little while. It's kind of messy. All you got to do is go second entry, the upper left, lower right, and it will bring this back up. And it's now editable. So just go in, put your cursor on that, change it to a minus, and hit enter. That way you don't have to retype this stuff, because that's what you want to do is subtract. So what is 3 minus 21 raised to the 1/4? 0.86. And just for my sake, and so that I know that you know, when you do this, put a dot on your equal sign, indicates that you know this is an approximation. Big Ideas doesn't require it, but if you're gonna do the assignment on paper, it's nice for me to know when I read it that you know and acknowledge that that's an approximation. Last thing, example 5. Can anybody describe to me the concept of depreciation? Anybody heard of that? It's an economic term, yes.
It's when you buy something at one price and over the course of years it loses its value.
Wow, that was awesome. That is perfect. Did you hear what he said? Anybody want him to repeat it?
You buy something for a price, then over time it is worth less.
It loses its value because it either because the technology is better for newer machines, or it just becomes obsolete like a car. You buy a car, drive it off the lot, immediately it loses value because now it's a pre-owned car, right? Machines are typically the ones that depreciate. You can save on taxes if you know how to use depreciation in your favor. Anyway, here's what's going on. And sometimes people have to know, they need to know now, what's it worth right now? So I know what to ask for it, or what I'm gonna sell it for parts for, or whatever. We've got a machine that's used in a hospital. So listen to the scenario. It says, a hospital purchased an ultrasound machine for $50,000. The hospital expects the useful life of the machine to be 10 years, at which time its value will have depreciated to $8,000. In other words, scrap it out for parts. Okay? But it will have a sale value of $8,000. Somebody will buy it for that much for parts. That's what we're assuming after 10 years. The hospital uses the declining balances method for depreciation. There's all sorts of depreciation methods, lots and lots. This is one they're using. You don't have to know what that means. So the annual depreciation rate, R, in decimal form is given by the formula. So there's a certain percentage rate. The value is, there's a certain percentage of the value that's lost every year. And according to this particular depreciation formula, R, which is the rate at which it's depreciating, is equal to, what is it?
1 minus parentheses S over C close parentheses 1 divided by N or 1 over N.
Okay, so we need to know what these things are because there's 1, 2, 3, 4 variables in this thing. So now they're going to tell us what things stand for. And it says, in the formula, N is the useful life. For us in this problem, it's 10. Okay. S is the salvage value. What's the salvage value? 8,000. C is the original cost. 50,000. What annual depreciation rate did the hospital use? How many variables did we have in this? 1, 2, 3, 4. How many did they give us? 3. They gave us everything but R because that's what they want us to find. And that's going to be 1 minus. What was the salvage price? Purchase price? That's what they told us C was. N is 10, so that's 1/10. Yeah, plug that in your calculator. This is the syntax you would use. 1 minus. You can plug it all in at once so you can see and make amendments if you want. But it's 1 minus parenthesis 8,000. Or if you want to reduce that fraction, you could say 8 over 50. Or even 4 over 25. Anyway, 8,000 divided by 50,000. If you want to put them all in there, raised to parenthesis 1 divided by 10. I realize that's 0.1, but I want you guys to get used to using the fraction. It's more inclusive. What do we get for R?
0.17.
0.17,
Yeah.
which translates to a 17% depreciation rate using this method. It loses approximately 17% of its current value every year for 10 years. They have 0.167. Why I have that, but so I'm going to put that up here. It'll tell you generally.
We rounded up, so.
Okay, it'll usually tell you in the stem of the problem what they want you to round it to. So if they want you to make a percentage rounded to the nearest tenth, this needs to be the nearest thousand, so that when you move this over, you've got a tenth there. So 16.7% depreciation. So it's a plug and chug problem. You understand what I mean by that? If you can understand what the variables stand for in the formula, you just plug them in. Make your calculator chug it out. Okay, make sure that you translate it at the end though, because R is as a decimal, and if they want the answer as a percentage, make sure that you make the switch. Okay, that was a lot of little pieces. I hope you got them all. You ready? Is anyone doing this assignment on paper? Okay, here it comes. By the way, anybody that's new to my class, if you're going to do an assignment on paper, The paper looks like this, and the holes are on the left. People, this is the front of the page. I want your assignment to start out on the front, with holes on the left. I don't care if you're left-handed. This is the front of the page. Put it on the front. There's a margin up here, and there's one underneath it here that forms a square right up here, and that's where I want. Oops. That's where I want your section number, and I want it big because I don't want to use my glasses all the time, and I don't want anything else in that box but that number, 5.1. Here's the assignment for those doing it on paper. It is number 1, 11 to 21, odd, 22 to 25, 27 to 33, odd, 34, 35 to 45, odd, and 49.